Alright, so this is our last lesson for Chapter 3. This is about applications of exponential functions. We're going to, in the textbook, it really was during 7.1 and 7.2 and 7.3 that they did these applications. So really, we could really rename this as 7.1 through 7.2, and it's all the application questions that we didn't do yet, so that we're going to take a look at. So if this is our function, just a reminder, a few things, that this base c is what the function is going to be multiplied by all the time. So when we're looking at these functions, look for a multiplier, and you'll see what I mean in just a second. So and a quick review, a is going to be your y values are multiplied by a, y values multiplied by a. Your b, your x values are multiplied by 1 over b, and then also we get a shift of h to the right and k up. So h to the right, or if it's negative, it'd be left, or if k is negative, it's down. Alright, so let's take a look at this summary of rice on a chessboard. Now you may not remember it, but it's actually from the beginning of our textbook. So back in 7.1, this characteristics of exponential functions. So they talk about the inventor of chess being asked to be rewarded for his invention by getting 1 grain of rice on the first square, 2 grains of rice on the second one, and then 4, and then 8, and then 16. So it gets multiplied each time. And so the ruler thought, hey, this is a great deal. He accepted it without really doing the math, and it turns out that it's a big pile of rice. So on the 32nd square, if you were to make a pile, that's the kind of size it would look like. So let's see if we can go back here and say, for our summary of our rice board, what's our multiplier? So in terms of our value of c, right? So our multiplier each time is that in this question, c is going to be equal to 2. Every single square, we're doubling the amount of rice. So if we were to make up a simple version of y is equal to c to the power of x, so in this case it would be y is equal to 2 to the power of x, so I'll change that to 2. Let's see what this would look like. So if we make a x and a y column here, so 2 to the power of x, 0 is equal to 1, 1 is equal to 2. Now those are our two common points that we are always aware of. If we put in a 2 for x, then we get a 4. And we see sort of the basic shape here is going to look, the basic shape is like this. Of course, now really for our chess pieces and the rice, the domain wouldn't go start at 0. It'd probably just start at 1. So it'd probably start at 1 and go up like that. Now is that a good model of the rice on the chessboard? So let's just think about this. If we say that, say, n is equal to the square, and so how much rice is there? So let's go back and take a look at it for a second here. So on the first square, you have 1 rice. On the second one, you have 2. So on the first square, we have 1 rice. On the second one, we have 2. And then on the third one, we have 4. So now when I make a comparison between these two, this would be my parent function. How does this one look a little bit different? Well, I can see that my x values are over 1. That makes sense? My x values are actually 1 higher all the time. So if I was going to compare the 0, 1 and the 1, 1, if I was to make a graph, say if I was to make this graph in green instead, it would be shifted over, and it would look kind of like this. It would be shifted over to the right. Instead of 0, 1, we'd have 1, 1. I did model this here over in Desmos, but before we do that, how do you shift something to the right one? how did we make our x values 1 larger? Well, that's our h value here, isn't it? If we want to have our h move 1 to the right, if we want to have our function move 1 to the right, we want h equal to 1. So we would say h is equal to 1. So instead of y is equal to 2 to the x, now the image, the new graph, try to do this in red, the image here, I'm running out of room, would be equal to y is equal to 2 to the power of, now see where the h goes, over here, x, try this again, 2 to the power of x, having some technical difficulties, I'll be right back. Okay, so we have y is equal to 2 to the x minus 1. So if I just make a little bit of space here, so my original graph, my parent was y is equal to 2 to the x, and then my actual function is y is equal to 2 to the x minus 1. And this is the one that will be the rice on the chessboard. So here's an example of going through the motions of saying, how can we make an exponential function to mimic rice on the chessboard? Now let's go to, well, I did do it in Desmo, so let's take a look at that here. So here is our original y is equal to 2 to the x, and you can see how that looks. And now if I add my y is equal to 2 to the x minus 1, then there's the graph, and you'll notice that 0, 1 gets shifted to the right, and 1, 2 gets shifted to the right, so we get our new points here. So that's the difference between having our 2 to the x and then 2 to the x minus 1. Alright, so moving over to my first example here, it's a photographer uses filters to change the look of the photographs she takes. A particular filter reduces the light transmitted through it by 100%. Okay, so if I was to get a sense of what's going on here, so we've got some amount of light that's shining, and then it hits a filter. I'll make this filter look yellow here. So it hits this filter. Now not all the light gets through, only 85% of it. So if the beginning amount here was 100% of the light, after it passes through that filter, we only have 85% of the light. So what happens if we add another filter? So if we add another filter here, clearly less light is going to be getting through. So how much would be at this spot over here? How much light would we get after 2 filters? Well, remember this is exponential functions, and let's think about what our multiplier is. Okay, so what did we multiply this number by to get that number there? If it reduces it by 15%, it went from 100 to 85, but it actually multiplied. If you think of it multiplication, it multiplied times 0.85. So for our next step here, we're also going to be multiplying by 0.85. So in our second step, I don't know, I'll have to get my calculator, 0.85 times 0.85. So I get 0. I guess I'll need my green here. Here at this point, it'd be 0.7225, so it'd be 72% when it's rounded off. So when we make our function now, we're going to say, okay, now we know that our c value is going to be equal to 0.85. So that's the thinking. When you see this, it's reduced by 15%. That means that we're going to be multiplying each time by 0.85. And our function, our base function, is going to look like y is equal to 0.85 to the power of x. Okay, our initial amount is 100%. So if I put in a 0 for the number of filters, let's just think. So let's say if n is the number of filters and p is the proportion of light. If I put in a 0, so I guess I should write this as p is equal to 0.85 to the power of n. If I use this function and I put in a 0 for n, 0.85 to the power of 0 is equal to 1. So that sounds great. If I have 0 filters, then I get 100%. If I have one filter, I'm going to get 0.85 to the power of 1, and this is my 0.85%. If I put in two filters, I'll get my 72%, or in fact it was 0.72. So the answer to the first question is right here, is this p is equal to 0.85 multiplied by n. Now it says graph the function. Use the graph to estimate the number of filters needed to reduce the light transmitted to half the original intensity. So when it says to graph the function here, and we're actually trying to use the graph to estimate, it's just fine to use something like Desmos for something like this. We can do a general sketch first of all, and we know that our first point is going to be 0, 1, and our second point is going to be equal to 1, whatever the c value is. So in this case it's 0.85. So those are two of the points that we can put in right away. So 0 is 1. Now 1 is 100%. So I can either put 1, or if I wanted to do it in terms of percent, I could do 100%. Either way. At 1, so I'll say that this is 0. Maybe I'll put this as 1, 2, 3, 4, and then 5. At 1 it's 85%, so let me just see there. There's 50, there's 75%, so 85% might be about here. So this point here is 1, 0.85. 2 was 72%, so if that was 75, it's just a little bit lower than that. 2, 0.7225 according to my calculator. If I multiply that value times 0.85 again, then we'll get 3 and 0.614, so just a bit more here. So we're going to be getting a curve, which is, it's not a straight line, it's going to be a curve, so it's going to get this kind of a shape to it. And at what point does it hit 50%? So this one here was 3, 0.61, and if I multiply that times 0.85 again, I get 4 and I get 52. So my graph is a little bit off, 4, 0.522. So I can't really say that this was a great way of using the graph to estimate, because I really threw in my values into a calculator and I multiplied this times 0.85, and then I multiplied it times 0.85 again, and so on to get each of my values. So my answer really is, it should be close to 4 filters. But there's no problem with taking this and putting it into Desmos, and let's try that. So if I go over here, we'll delete some of this stuff here. I can use this basic formula here, but instead of 2, I want to have 0.85 to the power of x. And then if I want to find out when this is equal to a half, I can just put y is equal to 0.5 and then see where they meet. And here, if I have a spot where they meet, and so my answer is 4.265. Now we really can't have 4.625 filters, so the answer is much closer to 4 than it is to 5. So you won't be having any questions where you require a graph to do this. We're going to be learning a mathematical way of finding all these, but what we need to do, the most important part, is to be able to figure out this p is equal to 0.85 to the power of n. Alright, let's look at example number 2. The half-life of a radioactive substance is 4 days. So what a half-life means is that we have some substance, and 4 days later half of it still exists. The other half is turned into something else. It's lost some neutrons, it's turned into a different isotope, and it has decayed. So whenever you see half-life, whenever you see, right away you can think c is equal to 0.5. Things are being multiplied by 0.5. So we're supposed to set something up where P is equal to the proportion after T days. So why don't we try this? 0.5 multiplied by T. So if we set something like that up, let's just try our function out. If we put T and then we put P over here, at 0 days we would still have 100% of it. After 1 day we would have half of it. After 2 days then we would have 0.25. This doesn't quite work out because the problem is this 4 days here. So what we really want to do is we don't want to have 0, 1, 2. We want to have something very similar. We want to have 0, 4, 8. And everything else should be the same. Oh, yeah. So really what's happening here? We are taking this 1 and we are turning it into a 4. In other words, we are taking our x values and multiplying times 4. So this 4 days piece means that we are going to be multiplying our x values times 4. And what happens? How do you multiply x values? Well, just a reminder from the beginning. Oh, I guess I erased all that. It's this b value. It's the b. So if we want to multiply our x values times 4, that means that b is going to be equal to 1 over 4 because you multiply your x values by the reciprocal of b. So instead of p is equal to 0.5 to the power of t, we want to change this to say p is equal to the 0.5 of, now you can write 1/4 t, or why not write it as, I'll zoom in a little bit, I'll see if I can write this better. How about we write it as 0.5 to the power of t over 4. Okay, and then that will give us this function right here. So this, let me do a little highlight, this one goes with this. Okay, and that will be your right answer. The last one says, use your function to determine the time that must pass until there is 25% of the substance remaining. So again, in this part we're going to have to use graphing technology. So we want to set this up 0.5 times t to the power of 1/4. So if I go over here, I'm going to say y is equal to, see if I can make this work, 0.5 to the power of, left parentheses, x divided by 4. Okay, and we want to compare that with, what was the value? 25%, so we want to put as our line to intersect 0.25. Oops. There we go. We should light it up. Okay, so where do they intersect? They intersect at 8, so that would be after 8 days. Oh, in fact, we had already done this, right? Use your function to determine the time must pass until there is 25% left, so that would have been right here too. So we actually calculated it because it was a rather easy one. Example number 3, the number of bacteria in a sample doubles every 10 hours. Initially there are 64 colonies present. Well, first of all, if something is doubling, that means that we know our C value is going to be equal to 2 because it's multiplying all the time. This 10 hours means that we're going to be multiplying our x values times 10, so B is going to be equal to 1 over 10. All right, so that's where this doubles every 10 hours, makes our b is equal to 1 over 10. Now the new twist in this one is, what about this? Initially there are 64 colonies present. Up until now we've always had 100% of something, and we've talked about proportions. So this will be our A amount. So this will be A is equal to 64. Let's try it out. Let's make a function here. So we're supposed to use the letter n. N is equal to, and our variable is t, so we're going to say 64 multiplied by our base, which is 2. So we'll go like this, 2 to the power of t over 10. Okay, so let's see if this works out. So if I have make a chart. If I make our t equal to 0, that means 2 to the power of 0 over 10, which is the same thing as 2 to the power of 0, which is 1. I would get 1 times 64, I would get 64. Okay, if I go 10 hours later, I'm hoping that it's going to double. So now I get 2 to the power of 10 over 10, so that's the same thing as 2 to the power of 1 times 64, which is 128. Yeah, it seems to work. Okay, so here is my function. Use your function to determine the number of colonies present after 24 hours. So n is equal to 64 multiplied by 2 to the power of 24 over 10 is equal to 64 times 2 to the power of 2.4. This brings up an interesting math idea, is like, how do you do powers with decimals? Like, how many times are you multiplying 2 by itself? How do you multiply 2 by itself 2.4 times? Well, we can actually do it. Our calculators will do the work for us. The best way to say how you do this is to graph 2 to the power of n and then look along the curve. But when you're actually thinking about what the definition of a power is, that 2 is multiplying by itself 2.4 times, it doesn't make quite as much sense. So anyways, I'm just going to plug it into my calculator. I'm going to say 2 to the power of 2.4, which is 5.278, and then I'm going to multiply that times 64, and so my calculator tells me that the answer is 337.7940 ... Determine the number of colonies. Can we have a decimal number of colonies? I think in a lot of these questions, you can leave it as decimals, but sometimes you have to think, does it make more sense to have it as a whole number? And I think this is one of those cases. So we should say 338, rounded to the whole number. Determine the time that must pass until there are 1,024 colonies present. So if we start off with our n is equal to 64 times 2 to the power of t over 10, this is an example where we're going to be solving for t. So I'll put 1,024 is equal to 64 times 2 to the power of t over 10. Looking at this in terms of powers of 2, 1,024 is the same thing as 2 to the power of 10 is equal to 64. Let me think. 2, 4, 8, 16, 32, 60. I think it's 2 to the power of 6. 2 to the power of 6 multiplied by 2 to the power of t over 10. So 2 to the power of 10 is equal to 2 to the power of 6 plus t over 10. So 10 is equal to 6 plus t over 10. Resuming my work over here, and maybe I'll switch to green for this occasion. So I will multiply both sides by 10. So when I multiply this side by 10 and this side by 10, I get 100 is equal to 60 plus t. I'll subtract 60 from each side and I get t is equal to 40. And what are my units for t? The time that must pass, and it's hours, so 10 hours. Okay. I'm going to stop now because the compound interest is a little bit different, and I'll see you back in a little bit.